In this lesson, we're going to study Descartes' rule of signs. Now, Descartes' rule of sign was developed by a person named Rene Descartes, and he was alive from 1596 to 1650. He was French-born philosopher, mathematician, and scientist, and he is generally considered the father of modern philosophy. Now, if you are taking a philosophy course, you may also have heard this, that he is also known for the statement, "I think, therefore I am." But anyway, Descartes' rule of signs was after many studies on polynomials, Rene Descartes came up with these rule of signs. And these rule of signs is very helpful. The Descartes rule of signs is very helpful in helping you to determine when you do the rational zeros test or the rational zero theorem to determine which of those zeros you might want to look at first. Okay, it doesn't tell you what to look at. Or it doesn't tell you which ones are the real zeros, but it can help you. All right, so let's continue with this. So you can use Descartes' rule of signs to determine the number of possible uh, positive real zeros, negative real zeros, and imaginary numbers. Now, when we talk about Descartes' rule of signs, you're going to be focusing on positive and negative. But knowing the possibilities for positive and negative, you can also discuss the imaginary zeros as well. Okay? All right. Now, Descartes' rule of signs provides more specific information about the number of real zeros that a polynomial can have. So, for example, do you remember when we looked at this lesson, which was called Real Zeros of Cubic Functions? There was a problem, example number 2, where you came up with all of these possible rational zeros. Okay, and there were quite a few. You see that? Then we use synthetic division to figure out that the zeros are actually 2, 3 halves, and 2, right? So there are only two. There are only two. Remember, 2 occur twice, so that's a multiplicity 2. But there were only 2 positive real zeros. See, there weren't any negative, right? There were no negative. So this statement here that says it provides more specific information about the number of real zeros that a polynomial can have. When we use Descartes' rule of signs in this lesson, you're going to see that it's going to tell you that you're going to have zero, none negative real zeros. And so if you know that there are no negative real zeros, then you would not even try any negative real zeros. All right. So I'm sorry, any possible negative zeros. You wouldn't try any of those. So you would stay with the positives. So it kind of helps in that sense. It helps you to determine if you have a lot of possible rational zeros to choose from, Descartes' rule of signs can help you to narrow this down. Okay, so you're going to see in this example, we're about to do this, but in this example from a previous lesson, Descartes' rule of signs will tell you that you have no negative real zeros. So you would not even try any of these negative possibilities. All right, so it's a very interesting uh, rule, um, but it is very helpful. It is very helpful. Most of the time it is, not all the time, but most of the time it is helpful. Okay, now let's look at the next part. Descartes' rule of sign is based on the number of variation, and another word for variation is changes in signs between consecutive coefficients. All right, so let's look at an example of what we mean by that. So what do we mean? What do we mean by changes in signs between consecutive coefficients? All right, so let's look at this example. So you see how you have, and by the way, it must be When you're using Descartes' rule of sign, it must be in descending order. Must be in descending order. All right, so when you are looking at the changes in signs between consecutive coefficients, you have to first of all make sure it's in descending order. Okay, so x to the 7th, x to the 4th, x cubed, x squared, x and -6. All right. Now, this particular one, this function has 3 sign changes. So let's see why it has 3 sign changes. So you see this coefficient is positive, this coefficient is negative. So you're going from positive to negative, right? So that's a change. So I'm going to denote it as this little curve here. Then from second to third, a negative, that's the same. So that's not a change. So far we only have one change. Then from the third to the fourth, from negative to positive, that's a change, right? Then from here to the next one, a positive to positive, that's not a change. They're both positive. And then from positive to negative, that's a change in sign. So notice I have 1, 2, 3. I have 3 sign changes. All right. So what that means you're going to see is that in terms of the possible positive real zeros, you can have at most 3. All right, so we're going to have the discussion about that. But first of all, I need to make sure you understand what we mean by sign changes. By changes in sign from between consecutive coefficients. So 1 to 2, that's a change, positive to negative. Second term to third term, the signs are the same, negative, negative. Then from this term to this term, negative to positive, that's a sign change. Positive, positive is not a change. And then positive to negative is a change. All right, so that's what we mean by sign changes. That's very important to understand that. Okay, now, so before we can look at an actual example using Descartes' rule of signs, we need to talk about what Descartes' rule of signs says. So Descartes' rule of signs says this. Given a polynomial function, and the polynomial function has real coefficients. Remember, a real coefficient, a real number is rational or irrational. All right. So that's what we mean by real coefficients. So given a polynomial function with real coefficients, there are 2 parts to it. 1, 2. Okay. So the first part talks about positive zeros. The second part talks about negative zeros. All right, so that's important to know. There are 2 parts. There are 2 parts to Descartes' rule of signs, positive and negative. So let's talk about the first part. So it says this: the number of positive real zeros of a function is either. So notice in both parts it's going to say is either, and you have A and a B part. Okay. Now you may say, well, that's too much to remember. No, it's not. The more problems you do, you'll see it's very simple. Very simple. Okay. So the number of positive real zeros of f of x is either the same as the number of sign changes of f of x. Okay. So it's either the same as a number of sign changes of f of x. So remember in this one right here. So here's my function f of x. There were how many sign changes? 3. So according to this, the number of positive real zeros is either the same as the number of sign changes. So it's either 3. Okay. So the number of positive real zeros that this function can have. Now remember, a real zero can be rational or irrational. Keep that in mind. Okay, rational or irrational. When we use the rational zero theorem, these are all rational numbers. None of them were irrational. Okay, so those are all rational. So always keep that in mind. So according to this, the number of positive real zeros of f of x is either the same as the number of sign changes or less than the number of sign changes of f of x by a positive even integer. So basically, all you're going to do is subtract 2. Subtract 2 until you get to 0 or a negative number. Because remember, you cannot have any negative zeros, negative real zeros. Let me rephrase that. So so the number of sign changes we said was 3, right? So you can have a function with 3 zeros. You can have a function with 2 zeros. You can have a function with 1 zero. You can have a function with no zeros. But you can't have a function with a negative number of zeros. That's what I mean. Okay? All right. Now, here's something else that's going to be important. If when you do this, the function has exactly one variation in sign, then that means that function has exactly one positive real zero. So you're going to see some examples like that. All right, now, so remember the positive real zeros is based on the variation in signs for your function. Well, what do we look at if we're trying to determine the negative real zeros? Well, you've had practice like this in a previous course and also in this course. You're going to look at f of negative x. So f of negative x. So you're going to figure out, well, first of all, what's f of negative x? And then you're going to look at the sign changes. And then the b part is the same as the b part here. So the number of negative real zeros of f is either the same as the number of sign changes of f of negative x or less than that by a positive even integer. And if f of negative x has exactly one variation in sign, then f has exactly one negative real zero. Okay? All right, so we're going to come back to that. So let's look at an example. Okay, so let's look at this example. Okay, so determine the possible number of positive and negative real zeros of this function. All right, now this function comes from a previous lesson we did, and let me kind of remind you what it looked like. So it was this one. So it came from a previous lesson. So you may recall this problem where we found all these possible rational zeros. Now remember, a rational zero is a real number. It's a real zero. Okay? And so when we did this, though, we found that there were only 2 positive real zeros that this function had. There weren't any negatives. So keep that in mind. So we're basically doing this example here. So determine the number of positive and negative real zeros. Well, according to Descartes' rule of signs, we have to look at both f of x and f of negative x. And we got to look at the variation in signs of the coefficients. So we got to look at 2 things, f of x and f of negative x. All right, so let's do f of x first. So we're looking at sign changes. So sign changes. So I'm going to rewrite f of x over. And so I have 2x cubed minus 11x squared plus 20x minus 12. All right, so sign changes. And this is going to be the sign changes for the positive real zeros. Okay, so let's look at this. So here I'm going from positive to negative. You look at the coefficients. Positive to negative 11. That's a sign change. Negative 11, positive 20. That's another sign change, right? Positive 20 to negative 12. That's a sign change. So there are 1, 2, 3 sign changes. So there are 3 sign changes. So what that means is this. So remember this. What it means is this. So the number of positive real zeros of f is either the same as the number of sign changes of f or less by an even number. So what that means is this. So the possible number of positive real zeros are, so here we go. Now listen carefully. You're either going to have 3 of them, or you're going to have, okay, or you're going to have, you subtract by 2. So subtract by an even number. So 2 is an even number, subtract by 2. 3 minus 2 is 1, or 1. Now you may say, well, can I subtract again? No, because if you subtract again, 2 minus 2 is a negative 1. So you can't have a number of positive real zeros being negative. It must either be 3 or a positive 1 in this case. Okay? So that's what you would write. So when they ask you to determine the possible number of positive real zeros, you're going to say the possible number of positive real zeros are 3 or 1. You're going to have 3 or you're going to have 1. Okay? Now let's talk about the negative. So sign changes for the negative real zeros. Okay, now this is where you're going to look at f of negative x. All right, so listen carefully. So remember, this is f of x, right? So let's find f of negative x. So f of negative x, and it's very easy to do. Very easy to do. So f of negative x is going to equal. So remember what you did to find f of negative x? Where we see the variable x, you substitute negative x. So we have 2 times negative x cubed minus 11 times negative x squared, right? Plus 20 times negative x minus 12. Now, some things I want you to remember. Whenever you're raising a negative number to an odd power, that's negative, right? Whenever you're raising a negative number to an even power, that's positive. Okay? So negative number to an odd power is negative. Kind of makes sense. Kind of makes sense, right? Because if you think about it, negative 2 to the third power is a negative 8. If you raise negative 2 to the fourth power, you're going to get a positive 16. So a negative number raised to an odd power is negative. A negative number raised to an even power is positive. All right, so here's what I'm trying to say. If I have negative x to the third power, do y'all agree that negative x to the third power means negative x times negative x times negative x, right? Well, a negative times a negative times a negative is a negative. So you get negative x cubed. X times x times x is x cubed. Okay? So negative x raised to the third power is a negative x cubed. So keep in mind what I'm about to say. So that's 2 times a negative x cubed, y'all agree? Minus 11 times, well, negative x squared means this. Negative x squared means negative x times negative x, which is a positive x squared. So that'll be times x squared plus 20 times a negative x minus 12. So 2 times a negative x squared is a negative 2x cubed. I'm sorry, 2 times a negative x cubed is a negative 2x cubed minus 11x squared. 20 times a negative x is a negative 20x, and then minus 12. See, a constant never changes. Okay, so this is f of negative x. Now also listen carefully. Whenever your exponent is odd, see that's odd here, whenever you're finding f of negative x, the term with the odd exponent, the sign changes. So 2 becomes what? Negative 2. You see that? 20, see x to the first, that's odd. 20 becomes what? Negative 20. Everything else stayed the same. Your terms with the even exponent stayed the same. You see that? Negative 11x squared stayed negative 11x squared because of what we discussed right here. And your constant negative 12 stayed negative 12. So the only coefficients that change for f of negative x are the coefficients where you had the term, the exponent of the variable being odd. 3 is odd, 1 is odd. So as we go through the next two examples, look at that. All right, so now let's talk about the sign changes. So I'm going from negative to negative, that did not change. I'm going from negative to negative. That did not change. I'm going from negative to negative. That did not change. All right, so there are no changes, right? So what does that mean? Okay, so that means the possible, so there's zero sign changes. Y'all agree? So that means that the possible number of negative sign, negative real zeros, excuse me, negative real zeros is 0. There aren't any. There are no negative real zeros. This function has no negative real zeros. This function has 3 or 1 real zero. Okay? That's what this says. 3 or 1 real zero. Now remember, one of the things we talked about, you see the degree here? So the degree here says you will have 3 zeros. They're either real or imaginary or a combination, but you're going to have 3. Well, remember when we did this, how many do you have? You have 1, 2, 3, 2, 3. Obviously 2 occur twice, but you still have 3 positive real zeros. And so that's what that says. So in this case, when you actually do the work, when you actually do this part here, you're going to see that according to Descartes' rule of sign, you're going to have 3 or 1 real zero, and you're going to have no negative real zeros. And you didn't have any, right? You only had 3 that were none were negative. All right, so that's how you answer this question. So determining the possible number of positive or negative real zeros using Descartes' rule of signs involves you looking at the sign changes for f of x and the sign changes for f of negative x. All right, so your answer, when you do give the answer, now here's your work. When you do give the answer, though, you're going to say this: the possible number of real zeros are 3 or 1. Always decrease it by 2. The possible number of negative, that should be positive real zeros here, of negative real zeros is 0. There aren't any. Okay, so that was example 1. So that was, let me put this as number 1. So that was number 1 for those directions. Okay, let's look at another example. Let's look at example 2. The more you do, the easier it gets. Okay, so let's do this function, and all we want to do is this function is determine the, just to remind you, determine the number, the possible number of positive and negative real zeros. Okay? All right, so determine the possible number of positive and negative real zeros. All right, so remember Descartes' rule of signs, there are 2 parts. You got to look at f of x, and you have to look at f of negative x. And then you look at the sign changes. Okay, that's all it is. All right, so let's first of all talk about the possible number of positive real zeros. So to determine the possible number of positive real zeros using Descartes' rule of signs, you look at f of x. Well, this is f of x right here. So I'm going to rewrite f of x, which is x to the 5th minus 3x to the 4th plus 3x cubed minus 9x squared minus 4x plus 12. And then you look at the sign changes. Now, first of all, make sure it's in descending order. That's important, in descending order. X to the 5th, x to the 4th, x cubed, x squared, x and constant. So it is in descending order. Now let's look at the coefficients. This is positive, this is negative. This is positive, negative, negative, positive, right? Okay. So I'm going from positive to negative, so that's a change. Y'all agree? All right. Then I'm going from negative to positive. That's another change. Then we're going from positive to negative. That's another change in it. I'm going from negative to negative. That's not a change. That stays the same. Then we're going from negative to positive. That's a change. So notice I have 1, 2, 3, 4. So 4 sign changes. Okay? Now, so what does that mean? According to Descartes' rule of sign, what does that mean? Well, that means that the number of positive real zeros of this function, so the number of positive real zeros will be either 4. So you may have 4. Now, remember the largest, the degree is 5, right? So altogether, you're going to have five zeros. Some may repeat, but you can have 5. And some may be real, some may be imaginary. Okay, always keep that in mind. But Descartes' rule of signs only talks about real zeros. That's all it does. Only talks about real zeros, positive or negative. All right, so I'm either going to have 4, or you may have, or the number may be less than an even integer. Okay, so what that means is I'm going to have 4. 4 subtract 2 is 2. Now you're going to see in a little while why we subtract 2. It's going to make sense in a little while. Why are you subtracting 2? Why not subtract 3 or 1? But you're going to see why we subtract 2. Why it says subtract by an even integer. Okay, so 4 subtract 2 is 2, and 2 subtract 2 is 0. And I stopped there because I got to 0. All right, so you can have 4, you can have 2, or you may not have any positive real zeros according to this. All right, now let's talk about the negative real zeros. So the possible number of negative real zeros. Possible number of negative real zeros. All right, so remember, you got to look at f of negative x, right? So let me first of all write f of x. So f of x is I'm going to rewrite this over, x to the 5th minus 3x to the 4th plus 3x cubed minus 9x squared minus 4x plus 12. And I'm going to do the work just to show you. So f of negative x, remember our discussion earlier? A negative number raised to an odd power is going to be negative. A negative number raised to an even power is going to be positive, right? Okay. So if you do the work like we did in the previous problem, you're going to do this. You're going to say, well, that's going to be negative x to the 5th minus 3 times negative x to the 4th. So wherever you see the variable x, you substitute negative x, and always put that in parentheses. Plus 3 times negative x to the 3rd minus 9 times negative x squared minus 4 times negative x, and then plus 12. Okay? I'm almost out of room here. But remember our discussion. A negative x to the 5th means, and let me use this sheet here. So a negative x to the 5th and means this. Negative x to the 5th means negative x times negative x times negative x times negative x times negative x, right? Well, a negative times a negative times a negative times a negative times a negative is a negative. X times x times x times x times x is x to the 5th. So that's just negative x to the 5th. But that was 1 hour discussion earlier. Remember that? So this could, see, this is odd right here. So that means that 1 becomes a negative 1. Remember that? And then negative x to the 4th is just x to the 4th. So since that's even, that means negative 3 stays negative 3. So minus 3x to the 4th. So negative x to the 4th is still x to the 4th. Kind of makes sense, right? If you have to do what I'm doing here, then you do that. Negative x to the 4th means negative x times negative x times negative x times negative x. Well, a negative times a negative is a positive times a negative is a negative times a negative is a positive. And x times x times x times x is x to the 4th. All right? And then using that same um, idea, uh, see, this is odd, right? So positive 3 will become a negative 3. And it kind of makes sense because look, see where I have 3 times negative x cubed, right? I'm sorry, 3 times negative x cubed right here. Well, y'all agree that's 3 times a negative x times a negative x times a negative x, right? Well, a negative times a negative times a negative is a negative. So that's negative 3, and x times x times x is x cubed. But you don't have to do all this work. You know that negative x cubed is negative x in parentheses cube is negative x cubed, and times 3 is negative 3x cubed. This will be positive, right? So it'll be negative. So since this is even, negative 9 stays negative 9. So negative 9 times negative x squared is a negative 9x squared. And then negative 4 times negative x is a positive 4x, and then plus 12. So remember our discussion. When you're finding f of negative x, and you go back to f of x, only the coefficients of the terms with the odd exponent changes. The coefficients of the terms with the even exponent stay the same. So look, 1 became negative 1. Negative 3 stayed negative 3. 3 became negative 3. Negative 9, see x squared, negative 9 stayed negative 9. X to the first, 1's odd, so negative 4 becomes positive 4, and your constant always never changes. All right, so now let's talk about the sign changes. I'm going from negative to negative, that stayed the same. I'm going from negative to negative, that stayed the same. I'm going from negative to negative, see negative 1 to negative 3 did not change. Negative 3 to negative 3 did not change. Signs are the same. Negative 3 to negative 9 did not change. I'm going from negative 9 to positive 4, that changed. Right? That's the sign change. Positive 4 to positive 12 did not change. So there's only one sign change. So one sign change. Okay, so what does that mean? That means that the number of negative real zeros is 1. And you might say, well, you're going to subtract 2? No, because if you subtract, remember this means that you're going to have one negative real zero. There's one of them. The number of negative real zeros and the number of positive real zeros cannot be negative. It must be positive or 0. So if you subtract 2, that's a negative 1. All right, so you're done. Now you remember a while ago it says this. How many sign changes were there? That was just one, right? That was just one sign change. So that means that if f of negative x or if f of x has exactly one sign change, then that means that your function has exactly, in this case, one negative real zero. So this means that when you do find the zeros, one of them will be negative. You will have a real zero that's negative. That's what that means. All right. So the possible number of negative real zeros is 1. In fact, you can take the positive off because you know that according to Descartes' rule of sign, you're going to have 1. Now let's talk about how you're going to write the answer. So the answer, you're just going to say this. You're going to say the answer. You're going to say the possible number of positive real zeros are 4, 2, or 0. The possible number of negative real zeros is 1. Okay. Now, since there, if you remember, there's only one variation in sign here, so that means that when you actually find the zeros, when you actually find the zeros of this function, you're going to see that there's only going to be one negative real zero. There will be one, and there will be a negative real zero, and it will be, and there will be just one. Okay, for positive real zeros, you may have 4 positive real zeros, you may have 2 positive real zeros, or you may not have any. Okay. All right. Now, let's look at this example. So that was number 2. Let's do one more. Let's do one more. See, it's not, the more you do, the easier it becomes. Okay, so let's look at one more. So we have this function f of x, and you want to determine the possible number of positive and negative real zeros. So according to Descartes' rule of signs, we're going to look at 2 things. So we're going to look at f of x, and we're going to look at f of negative x. So remember, f of x will help you to determine the possible number of positive real zeros. So let's do that first. The possible number of positive real zeros. So we're going to look at the sign changes. So f of x is 3x cubed minus 4x squared plus 5x minus 1. Again, make sure it's in descending order. And it is x cubed, x squared, x, and constant. All right, we got to look at sign changes of the coefficients from consecutive terms. So from 3, see this is 3, negative 4, that's a sign change. Negative positive, that's a sign change. Positive to negative, that's a sign change. Okay, so in this particular case, there are 3 sign changes, right? 3 sign changes. So what does that mean? That means this: the possible number of positive real zeros for this function will be either, so you'll have either 3 or subtract 2. 3 subtract 2 is 1. You have a 3, you'll have either 3 or 1. Okay? All right. You either stop at 1 or 0. Don't say 3, 1, negative 1, because you can't have a negative number of zeros. You're either going to have 3 zeros or you're going to have 1 0. Okay? Now, so when you actually find the zeros, you either so when you find the zeros, you're either going to have 3 of them. Remember, the exponent's 3, right? So if they're all positive, you're going to have 3 of them. Or you may have 1 that's positive. That's all that's saying. Okay? So you're going to have a positive real zero, because you don't see 0 here. You see 3 or 1, right? So that means you're going to have 3 positive real zeros, or are you going to have just 1 of them? Okay, that's all that says. All right. Now, let's talk about the possible number of negative real zeros. All right, so I'm going to rewrite f of x over again. So here's f of x, 3x cubed minus 4x squared plus 5x minus 1. So if I'm going to determine the possible number of negative real zeros, I got to find what f of negative x is. So where we see the variable x, you substitute negative, right? But now some of you can skip the following step because look, you can go from here to here. I just remind you. So you know that the term that contains the odd exponent, all that changes is the coefficient. So when I find f of negative x, 3x cubed becomes a negative 3x cubed, doesn't it? The exponent that's odd stays the same. Negative 4x squared stays negative 4x squared. X to the first, that's odd, so 5x becomes negative 5x, and your constant stays the same. Okay? Makes sense, right? So you can skip this part. You can go from here to here. Just be careful. Now let me show you, though, what's really happening. So where we see the variable x, it's substituting negative x. So 4 times negative x squared plus 5 times negative x minus 1. And so remember, negative x cubed Negative x in parentheses cubed means negative x cubed. So negative x cubed times 3 is a negative 3x cubed. A negative x times itself is a positive x squared. So negative 4 times x squared is a negative 4x squared. A positive 5 times a negative x is negative 5x. Okay? All right. Now let's look at the sign changes. Negative to negative, that's not a sign change. Negative 4 to negative 5, that did not change, right? Negative 5 to negative 1, that did not change. So there are no sign changes. No sign changes, right? No sign changes. So what that means then is this: the possible number of negative real zeros is 0. So that means that means that f of x will not have any negative real zeros. That's what that means. You're not going to have any of them. So what that means is that when you use the rational zeros theorem, don't try any negatives because that says you don't have any. So you're just going to try the positive because this says you will have at least one of them. You either have 3 or 1 of them. So when using the rational zero theorem, just try the positive ones. See if any of those work because it says you'll have at least one. Now remember, this says real, so it could be the rational or it could be an irrational number. And remember, whenever you talk about the rational zeros theorem, those are rational numbers that you're looking at, not irrational. Okay? Now, I want to use that same example, and I want to try and discuss with you why we subtract by 2. So we either, remember you had 3 sign changes, so your answer is going to be either 3 subtract 1, 3 subtract 2 is 1. So let's talk about that. Okay, so listen carefully. Okay, so I'm going to rewrite this function over. I'm going to rewrite it over. So that's this right here. So all I did was just rewrote the function. And a couple of things I'll remind you. Remember the degree is 3, right? So the degree is 3. That means you're going to have 3 zeros. So since the degree is 3, f of x will have 3 zeros. Now remember, I said 3 zeros, so that could be either real or imaginary or a combination. Okay? And remember, sometimes the real zeros can repeat, so that's where you have that multiplicity. But regardless, you're going to have 3 real zeros. That's what that means. Okay. Now, remember we also talked about this. So from one of our previous lessons, you remember it said this. Recall from a previous lesson that the complex numbers, the imaginary numbers, occur in conjugate pairs. So if you have real coefficients, and these are real numbers, 3, -4, 5, -1, those are real numbers, then if you have any imaginary number, then its conjugate will also be a 0 as well. All right, so they occur in pairs. So that's why we subtract by 2. That's why we went from 3 to 1. We subtracted by 2 because of this. The fact that imaginary numbers occur in pairs. So the number of imaginary numbers will be an even number. All right, so let's look at this. There's something called the conjugate roots theorem. Conjugate roots theorem, or the conjugate zero theorem. And the conjugate zero theorem says this: if you have a function, a polynomial function with rational coefficient, remember rational is a real number, then the irrational roots occur in conjugate pairs. So if you have a plus the square root of b, then you're going to have a minus the square root of b as a 0 or a root. The same thing with complex roots, so the ones with the imaginary numbers. If a plus bi is a complex root, then so is a minus bi. So that's called the conjugate zeros theorem or the conjugate root theorem. So just remember, if you have real coefficients, real real coefficients, what I want you to remember for this is that for imaginary number, they're going to occur in pairs. Okay, real coefficients. All right. So if you have a plus bi, then a minus bi will be a0 as well. All right. So how does that help us? Well, remember in our example that we're doing here, so remember the possible number of positive zeros are 3 or 1, right? Remember that? And then the possible number of negative real zeros are 0. So if I look at this in terms of a table, I have positive zeros, I have negative zeros, I have imaginary zeros, and then the total. So according to my degree is 3, so I'm going to have a total of 3 zeros, right? According to what we did with this example, we're either going to have 3 or 1 positive zeros. So 3 or 1. So you put 3 or 1 there. For negative real zeros, there aren't any. So you know you're going to have 0 straight down because there aren't any. Okay? So remember, I have 3, right? So there are 3 positive zeros. If there are 3 positive real zeros, then you've reached your total. So that means I cannot have any imaginary zeros. Okay? Now remember, I can have 3 or 1. But what if I have just one? What if I have just one positive zero? Well, I know I can't have any negative, so that means I'm going to have 2 imaginary zeros. So 1 plus 2 is 3. Okay? So notice that the imaginary zeros, you keep increasing by 2. 0 plus 2 is 2. For the positive, in this case 0, you're not going to do because you can't go any lower than 0. But 3, I can subtract 2. So you keep subtracting 2. And once you get to 1 or 0, you got to stop. So what that means is this. When I do this example, when I actually find the zeros, these are the only 2 possible cases. Possible case 1. So I can either have 3 positive zeros, okay, or I can have possible case 2, where I can have 1 positive zero, real zero, and 2 imaginary zeros. Okay? All right. So in the next lesson, we're going to do more examples like this, but in the next lesson, we're going to focus on this table. So in the 3 examples, we did, we were only focused on determining the possible number of positive and negative real zeros. All right, and then you saw how to do the work and how to write the answer. In the next lesson, we're going to talk about the imaginary zeros as well. So you're going to look at this in terms of a table. Okay? All right, so that is the end of this lesson. So all this lesson you wanted to do was to find again the possible number of positive and negative real zeros. Okay? And that's all you wanted to do. So that is Descartes' Rule of Signs. So that's the end of this lesson.